All right, welcome to The Explainer. Today we're going to dive into something, well, kind of mind-bending. The idea that hidden inside a purely abstract mathematical proof, there could be a real working computer program just waiting to be discovered. It's a concept that's totally changing how we think about logic itself.
So let's just jump right in with a question that, honestly, it sounds like something out of a sci-fi movie, but I promise you it's at the absolute core of modern logic and computer science. The basic idea is, what if, when a mathematician proves something exists, they're also accidentally writing the code to go out and find it? So how is this even possible, right? Well, to get our heads around it, we first have to talk about this weird little paradox in math, a problem you could almost call the ghost in the proof. And it all kicks off with a very strange type of argument.
Okay, so here's the deal. Logicians have this term, a non-effective proof, and it's exactly what it sounds like. Imagine someone writes a perfect, flawless proof that a massive treasure is buried somewhere on the planet. You know for a fact it's out there, but the proof gives you zero clues. No map, no coordinates, nothing. That's a non-effective proof. It's a guarantee without a guide.
And this right here, this lays out the whole dilemma perfectly. On the one hand, you get this rock-solid promise. Some object exists, or a solution is definitely out there. But on the other hand, the how, the actual method to find it, the solution itself, is completely invisible. It's there, but it's hidden. And you can imagine, for a computer scientist, that is an incredibly frustrating situation to be in.
The reason for this whole mystery, this split, is because math, well, it kind of has two different personalities when it comes to logic. Two totally different philosophies about what it even means to prove something.
So let's paint a picture here. On one side, you've got the builder. This is constructive logic. For the builder, a proof is a recipe. If you want to prove a house exists, you have to give me the step-by-step blueprint. Every single proof has to be an algorithm. But then you have the oracle. This is classical logic. And the oracle doesn't need to show its work. It can use these clever indirect methods like proof by contradiction to just declare the house exists. Trust me. The guarantee is airtight, but the blueprint, it's nowhere to be found.
This leads us to the big one, the million-dollar question, really. Are the oracle's blueprints locked away forever? Or is there some kind of key, some way to force the oracle to reveal its secrets and translate that mysterious guarantee into an actual usable blueprint?
And what's so incredible is that the answer is a resounding yes. For decades, some really smart logicians and computer scientists have been creating these decoder rings, powerful techniques to systematically pull out the hidden code from these proofs that look, on the surface, like they have none.
So the first big idea is basically to become a translator. The whole goal is to take the oracle's cryptic, classical language and just meticulously convert it, line by line, into the builder's clear, step-by-step instructions.
One famous way to do this is called the Goal-Jensen negative translation. Now, you don't need to know all the nitty-gritty details, but think of it like this. It's a tool that carefully rephrases every statement in the proof. It turns "this thing exists" into "it's impossible for this thing not to exist." It's a subtle change, but that little shift forces all the hidden logical steps out into the open. And boom, what you get is a brand new constructive proof. And because it's constructive, the program is just sitting there, ready to be picked right out.
Okay, so that's one way. But there's another, more direct approach. It's called proof mining, and it is exactly what it sounds like. Instead of translating the whole thing, you just dig into the proof and start pulling out the useful computational bits.
And this stuff is seriously powerful. We're talking about pulling actual concrete numbers out of these super abstract arguments, or finally finding that specific witness that a proof only promised existed. It can even generate algorithms from proofs that are talking about infinity. It lets us find the computational gold without having to rewrite the whole map.
So when you crack these proofs open, what you find is something, well, it's absolutely profound. This isn't just some neat party trick or a clever translation game. It points to a deep, fundamental property of logic itself, a kind of beautiful symmetry between the act of proving and the act of computing.
This deep connection has a name, the Curry-Howard isomorphism. It's a cornerstone idea in modern computer science. And what it says is that a proof isn't just like a program. In a very real structural way, a proof is a program. A proof that you can sort a list is, quite literally, the sorting algorithm itself. The proposition is the type, the proof is the program.
Now, for a long time, everybody thought this proofs or programs idea only worked for the builder's constructive logic. It was a roadblock. But then, this logician, Michel Parigot, comes along, and he develops this new logical language, the lambda-mu calculus, that could finally make sense of the oracle's tricky reasoning. And with that, he gave us a solid algorithmic way to understand classical logic, unlocking its computational power for good.
And here is where it gets just wild. The programs we pull out of these classical proofs, they are just clunky copies of the constructive ones. Nope, they have their own unique superpowers. They can naturally represent the kind of complex control flow, the ifs, thens, and loops you see in everyday programming. Some of them can even be read as parallel programs, designed to run multiple calculations all at the same time.
Okay, so this is all super fascinating if you're a logician, but why should you or I care? What's the point of all this outside of a university classroom? What is the real-world impact?
Well, what all of this research really does is it builds a bridge, a really important one. It connects the most abstract, philosophical kinds of reasoning that humans do directly to the very concrete, very real world of software, algorithms, and everyday computation.
And the applications here, they're total game changers. I mean, imagine you write a mathematical proof that your software is bug-free. This process could then automatically generate the perfectly verified code for you. We could even discover brand new, super efficient algorithms just by looking at old math proofs in this new light. It just completely changes what we think logic is for.
This quote really nails the huge shift in thinking. Logic isn't just a tool for asking, is this true anymore? It's a blueprint for computation. A proof isn't just valuable for its conclusion, it's valuable for the program that it's secretly holding inside. And verification stops being about checking the logic and starts being about running the code.
Which leaves us with this final, really provocative thought. For centuries, we've looked at mathematics as this universe of abstract, unchanging truths. But what if it's also something more? What if it's a huge library filled with powerful, elegant programs, and we've only just found the library card? What other secrets are in there, just waiting for us to figure out how to read them?